I'm free, you know, I'm paid to lecture, and I can do this for 8 hours a day if you want. But okay, I'll
The
go.
more
I'll
the
do
more
my
you
thing.
speak, the more what you say becomes like a Gaussian, and so then we're losing.
That's right. I
Yeah,
mean, the
we're
more
losing
I
something.
speak, the more random everything sounds, and you're totally saturated by wisdom or lack thereof. So what do we know about the distribution, probability density distribution? One thing we know, it's probability, and it should be positive or at most zero, but it cannot be negative unless you're thinking very seriously. Like, let's say, Richard Feynman, who did define negative probabilities. Other than that, a priori, it's arbitrary. You know, depends on particular context experiments. But you have to require a few things for this to be a probability density. I'll require three things. I want it to be normalized. I want to be able to define a mean. And I want to be able to define its variance. In other words, whatever this function is, when I integrate over all possible states and average over number one, meaning just integrate over the thing, I should get one. If I look at my random variable and average over its probability of happening, that is called the mean. It's some number. And I also want to be able to define expectation value of the second moment. And that, as you remember, was mean squared plus variance squared in probabilist language. This thing can be anything. So it might take information and be arbitrarily large. But the question is, you know, can I find least information? You know, what distribution? The answer is minimize Shannon information, subject to constraints. It can be any function, but it should be normalized. It should have a mean and it should have a variance. And now here comes something that I regrettably haven't done. So you can force me to give an off-hours lecture on Lagrange multipliers. So how do you do this? You introduce, instead of this function, consider function, let's call it C function of rho, which is Shannon entropy. Remember, Shannon entropy is just minus expectation value of the logarithm of your probability density average. But now we require, this thing is called Lagrange multiplier. The first one, we require that integral equals 1. So this is the first constraint, plus second constraint is the parameter I call mean. plus the third constraint is that delta x, x squared, second moment, is mean square minus variance square. And now we are allowed to vary these three parameters, and we are looking for the extremum of this new function as I vary all possible distributions. And now, I'm doing a number of things I should have done in this course, but life was too short and we didn't do it. But you might have learned it in your mechanics courses or statistical mechanics. So basically, varying the distribution means I get rid of the integration and I just get out what's in here. So from the first guy, I get only the integrands, So the first integrand is log rho plus 1 log rho comes from here, plus 1 comes from there. Now from here, I only pick up lambda 0 from this term. From here, I pick up lambda 1 times x, the integrand. And from here, I pick up lambda 2 times x squared. And we are looking for this variation being 0. So the solution is, now what you do is you substitute this function in here, and you get expressions for Legendre constraints. And the result is that you find a distribution that minimizes Shannon entropy. As the form rho equals. I realize that I'm leaving you with lots to do if you don't know about Lagrange multipliers. But the answer is Gaussian again. So that's what's very special about Gaussians. Okay, I'm done.